Okay, so hello, and thank you for coming. Thank you for being on Zoom. So this is the second part of my lectures on the Keane-Smorodinsky proof of the Ornstein theorem. I should mention that if you're watching this on Zoom, I'm aware that the visuals are not as crisp. I sort of like made a trade-off. I wanted more space, and I had to lose focus a little bit. So let me remind you the setup and the notation. I have A, B, positive integers, and let me use A underscore for the set with A elements from 0, and likewise for B bar. And then I have X, which is the set of bi-infinite sequences that can be written using symbols from A, and likewise for Y. If I have a probability on A, let's call it P, then let me denote by P hat the product measure defined by it. So this is a measure product, this is a probability measure on X. And likewise, if I have a Q, that's the probability measure on this finite set, then I have Q hat, which is going to be the product measure on Y. I have a dynamical system, which is a shift on X and likewise on Y. And so I have P hat sigma X on X and Q hat sigma Y acting on Y. And we have the entropy, the so-called Kolmogorov-Sinai entropy of this type of maps. These are called we call Bernoulli schemes. The entropy of this is also the H of P, which is defined as this sum. And the Ornstein theorem said that P hat sigma X is measure theoretically isomorphic to Q hat sigma Y if and only if the entropies match. We discussed how this implies this last time. This was how, or why, one of the reasons why Kolmogorov defined this notion of entropy as an invariant. And we said that we defined this more strict notion of isomorphism for dynamical systems, which is this Ash topological isomorphism. And Keane and Smorodinsky really showed that if P hat sigma X is isomorphic in the sense of Ash topology to Qy, this is equivalent to the entropy being the same number. And recall that I was using this symbol, Ash, to denote almost everywhere. And perhaps I should write that down because that was one of the things that I had promised I was going to go more into detail. Let xy be compact metric. Mu and nu be probabilities. And let's say that we have a partially defined function from x to y I call it Ash continuous. If there are full measure subsets x0 and y0 such that when restricted to this x0 with respect to the subspace topology, it becomes continuous. To be more rigorous, I should be worried about the domain of this function, and I should be taking the intersection of x0 with the domain and blah, 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 but let's not worry about that. And if I have an Ash continuous function whose inverse is also Ash continuous, that's called an Ash homeomorphism. Now, in the context of shift spaces, so this can be made sense for when you have a bare space, or if you have a certain partition fixed on your standard space. You can again make sense of this. And it will be important for us. Observation. In our setting, so if X is the space of bi-infinite sequences with symbols coming from A under bar, and likewise for Y, then mu any shift invariant measure on X and nu any shift invariant measure on Y probability. And let's say that I have a function from partially defined function from X to Y, then the following are equivalent. Y is Ash continuous. 2, there's a measurable function, J, let's call it, on X, taking integer values, such that for almost all X in X, let's call it X star, for almost all X star in X, let me write it like this. For almost all X star in X, if for all I less than J star, and for all X in X, if the ith entry of the set of this sequence matches with the one that you chose, then the 0th coordinate of the image of this point matches with the 0th entry of the image of X star. So you have a map phi taking sequences to sequences, or ticker tapes to ticker tapes, and in order to be able to read the 0th coordinate, or any finite many coordinates, of the image of a sequence, or of a point, all you need to do is to look at finitely many entries in the image. This is one way of saying this. So perhaps I should write it like this. Let me just compress all this. For almost all X star in X, 0th coordinate of the image, when restricted to the cylinder set, to these entries, put the appropriate entries coming from X star. So this is a cylinder set. And I'm looking at the 0th coordinate. This is constant. Okay. So this is the second way of thinking about it. The third way of thinking about it is this. I should say here. And this is a semi-conjugacy. Otherwise, just looking at the 0th entry will not work, will not be sufficient. The third entry is that for all, let's call it I in B, if I were to look at an element of the standard generator of Y, which is a cylinder set, and if I were to look at its preimage, there's a countable collection, C sub I of cylinder sets of X such that up to a measure mu, the preimage of the cylinder set defined by putting the ith symbol, so the symbol I, to the 0th coordinate, is the union of the CIs. C and CI, C up to a measure mu. Okay, so this sort of like is perhaps useful in the context of the specific shift spaces. The third characterization is useful in the context of when you have dynamical systems on standard measurable spaces with fixed generators. And you just open up the definition. Of course, if I didn't put here this shift invariance or shift equivariance, instead of saying I need just one measurable function, I would need to say that for all finite subsets of spaces, I need a measurable function that does this. The fact that this is shift equivariant means that this just tells me that I can get any finite code for the image by looking at finite many codes in the entry, or in the input. Okay. So any questions about this so far? Yes. Oh, okay. So we're gonna move on. So this is sort of a nice way of thinking about this. I would like to say a couple words about something. So here this J is an important thing. So this function, so there is such a function if you have Ash continuity, and if you have Ash homeomorphism, if you have an Ash homeomorphism that conjugates the two actions, then you also have that the inverse, for the inverse, you also have another J that is quite possibly a different function. And then you look at the least J measurable function that does this, and that gives you the so-called coding length function. Okay. So J tells you, so minimal J is the minimal number of entries one needs to read to determine the 0th coordinate of the image. coordinate. And let's call this minimal j the coding length function. It turns out that in the case of the Keane-Smorodinsky isomorphism, we do end up constructing an Ash homeomorphism between the two shifts. But the coding length function of that is never going to be L1. So this is by Perry. And I'm just going to call it J again. The J of the Keane-Smorodinsky phi is not, well, is L1 if and only if, in fact, Q is a permutation of P, which is a trivial case. Q is a permutation of P, which, like we discussed last time, is if and only if, in fact, there's a homeomorphism that is defined everywhere between the two shifts that takes the measure to the measure. So this is like too strong, as you see. What is interesting is that, so there's behind us like a cohomology equation, and Perry is able to find, it turns out that there is something called the information co-cycle, which is like something very natural from an entropy theoretical point of view. And these two are functions. You're thinking of them as potentials. And Perry figured out that the two information co-cycles of the two systems being cohomologous is equivalent to the systems being Ash homeomorphic. And then the transfer, the regularity of the transfer, ends up being related to the regularity of this J function. In this case, if the J function is L1, then the information co-cycles end up being cohomologous with a measurable transfer, bounded measurable transfer. If it's if it's in Orlick space L log L, then it becomes something else, and so on. So it's very interesting. What is further interesting is that Serafin verified a claim that Keane-Smorodinsky made back in the day. After 20 years later, they made that statement. The J function of the one-sided Keane-Smorodinsky map. So I'm not looking for Ash homeomorphism. I'm looking for an Ash continuous map from one to the other one, and yet another Ash continuous map from the second to the first. This is sort of like the analog of the isomorphism. The J function of the one-sided Keane-Smorodinsky semi-conjugacy is L1. And so this was a claim stated as a theorem without proof by Keane-Smorodinsky back in the day. This is like super interesting as far as I'm concerned. And there's a lot of further work about invariance of Ash homeomorphisms or Ash equivalences by Schmidt, Tunjal, and other people. Very interesting stuff. So any questions about this? So this is a broad way of, general way of thinking about it in terms of topologies. This is sort of like a more explicit way of thinking about it. And it turns out that this J function, the coding length function, has further structure that tells you something about the regularity of solutions of the cohomology equation, or some cohomology equation. Let's put it this way. So, okay. So now I'm going to start talking about some other thing that we're going to need, some combinatorial stuff that we're going to need. that sort of like comes into play toward the end of the proof. But I think it would be good to introduce them early on, because that's sort of like the one of the big parts of the proof. One part of the proof is the Shannon-Macmillan-Riemann theorem, or being able to apply it in a nice way. And the other part is to be able to handle the combinatorics. And so Peterson calls this sociology because it's all about these maps called societies. I'm just going to call it combinatorics. So this is associated to the marriage lemma. Societies, and let's also write couplings. So I'm going to start with two finite sets. Let's just set that aside, what we've discussed so far. Let A and B be finite sets. Alpha be a probability measure on A, beta be a probability measure on B. I'm going to call a map a society, and I'm going to denote it like this. S from A alpha to curly arrow B beta is a function between the power sets, so collection of subsets, is a function such that a couple of things need to happen. First of all, I need to have a splitting property for all E, a subset of A. S of E should be the same thing as the union of S of A, where A varies over E. Second of all, I need to have some sort of very strong absolute continuity property. That is to say, for all E subset, measure of E should be dominated by the measure of its image. Okay. So property 2 is strong, that's how I imagine this, strong absolute continuity. And property 1 is telling you that in order to define a society, you don't need to look at this power set of A. You can just say, I have a family of subsets of B parametrized by elements of A. That's sort of a way to think about this. Another way to think about this is to think of them as sort of reverse hash functions, if you want. So S of A, I'd like to imagine as all those elements of B that I would hash into the bucket named A, and so on. And yet another way of thinking about this is where the name marriage comes from. You're sort of imagining A to be the set of boys and B to be the set of girls. And for A, a boy, S of A is the collection of all the girls that A likes. That's sort of like the interpretation that Peterson gives. And this is sort of like a very classical combinatorial thing. I'm not going to use this intuition that much. It confused me more, so I just left it alone. So this is this. There are a couple sort of associated constructions. If I have a society, then I have the dual society, which I'm going to denote by S star. It goes from B beta to A alpha, and S star of B is the set of all those A's such that S of A contains B. Refinement, if I have two societies from A alpha to B beta, I'm going to say that R refines S, and I'm going to denote it like this, R arrow S, if for all A and A, R of A is a subset of S of A. Perhaps I should mention this. If you were to plug in here E equals A, this is going to be 1, which means that the image of any society is going to cover. So this is sort of like a certain type of covering. What else? Refinement. Okay. Collision number. This is also called the promiscuity number for a society. If I have a society, its collision number also called the promiscuity number, is this. I'm going to do it like this. Gamma of S equals the number of B's such that the cardinality of S star of B is at least 2. Okay? So just to open this up a little bit, so this could happen only if you have 2 points, A1 and A2, that are not the same in S star of B, which means that B is covered, B is included both in S of A1 and S of A2. So this is S of A1, this is A2. So in a sense, this subset collides with this subset, at least here. So that's why I call it the collision number. And the marriage lemma is telling you something about being able to refine societies in such a way that this becomes nice. Okay. Examples. One example comes from couplings. I think this is sort of most natural ones. But it is not true that all societies are defined by couplings. Let me just define what a coupling is. So let's write it like this. Example. Let lambda, so I fixed A alpha and B beta, let lambda be a probability measure on A times B. I'm going to have some assumptions here, but let's define S sub lambda from A to power set of B by taking A to all those B's in B such that lambda of A B is positive. I'm going to put here assumptions. If something happens, then this is going to be a society. If this, then S sub lambda is a society. In order for S to be a society, I'm just going to first do this. Oh, yes. Yes. Exactly. Yes. Yes. Yeah, so if you want to think of it this way, societies are generalizations of joiners. In this case, for now, we're looking at finite So we're looking at maps between finite sets, but the reason that is happening is because we're going to take this machinery and plug it into the proof. And then because this is sort of between finite sets, it's going to help us build the isomorphism that is shift invariant. That's sort of like the idea. But yeah. So I'm going to first do the proof of this example of this statement, and then based on the proof, I'm going to write down the assumptions. If I have a subset E, what I want is that I want S of E in measure to be larger than alpha of E. Okay, so let's try to open this up. I can write this like this. So this is the sum over all those B's in S of E of beta B. But then let's say this happens. Push forward of lambda to B is this. Let's say that if I were to push it forward, the weights that this push forward associates to any element in B is less. So that's going to be my first assumption. For all B in B, this, let me also perhaps write down what that means. So the space of, so the category of measure spaces does not admit products, and that's sort of like the main issue here. You're sort of like somehow using the categorical pathology to do things. So I have here A times B with lambda, and I have the product, I have the projection to A, and if I were to push forward lambda, I get a measure here, and I have likewise here another guy. And this measure, for instance, is just the marginal, right? It's like you take the sum over all B's of lambda of AB. The picture is that, so this is A times B. This is A, and then this is B. You have here a point, A, and in order to figure out what the push forward measure gives in measure to this, you just look at the fiber and add all the densities up. And likewise for this guy. Okay? So I'm saying that if instead of equality, I have inequality, this is still true, and then this is equal then to this, but then you see, so this is the integral of, or the measure of A times S of E. But then this is a superset of the graph of lambda, if you want, AB, such that B is in S of, oh, sorry, A in E, B in S sub lambda of A. So I forgot lambdas here. So by Fubini, I can change it to, let's call this gamma. Gamma sub lambda of E. So this is lambda of A times S sub lambda of E, which is like this. But then, if I were to fix a point A, B is in S sub lambda of A if and only if the measure is positive, lambda AB, but then I can just contain the whole fiber. So this is in fact really lambda of what am I trying to say here? Oh yeah, sorry. So this is like this. Sum over A in E and B in S sub lambda of A. Okay, but then this is the same thing as lambda of E times B, which is the same thing as, oh wait, here's what I need. Okay, so now at this point, I want to use the other one and write it like so. B in B alpha, oh, lambda AB, and then this is the second marginal. Okay. Push lambda to A of A. So here I need, so this is equal actually, and then this I want to dominate alpha of A, so that the second assumption is that if I were to push lambda onto B, onto A, it should dominate alpha. So if my probability measure is such that if I were to push it onto the first guy, I'm dominating the internal measure, and if I were to push it onto the second guy, I'm dominated by the internal measure, then the map S sub lambda defined as this thing becomes a society. In particular, if it were the case that I had equalities here, that is to say, if my lambda was a coupling of alpha and beta, then I would have a society like this. Okay. Okay. So, any questions about this? This took longer than I thought. So let me call any probability measure lambda that satisfies these two things a subcoupling oh, lambda is a subcoupling of alpha beta if this happens, and coupling if you have equality. So that here you can replace this by alpha and that by beta. Okay? So we know how to write, how to come up with couplings or subcouplings. This gives you many examples of societies, but not all societies. Probably most societies are not induced by couplings or subcouplings. You can just do a combinatorial argument to see this. But this is that. Okay, so this is an important thing. Let me say more things about societies and their structures. Observation. Oh, wait. So now that I said this, yes, I can define product. Oh, before that, I should do this actually. Sorry. Observation. If I have a society then there is a coupling lambda of alpha and beta there's a subcoupling, let me be safe, subcoupling of alpha and beta such that the society defined by the subcoupling is refining S. So basically you start with a society, you can sort of get rid of points, get rid of collisions, and eventually you get a subcoupling. And this is sort of like an interesting thing. If I have time, I might get into the proof of this. This is nice. And slightly more trivial is if S, if T is a function and there's a coupling, there's a society, and there's a society yes. So I think that this comment is about the question of the product is the example I already used. Oh yeah, so I did not understand the comment about the products of probability spaces. Was this essentially that space of probability measures on a product of spaces is not equal to product? Yeah, so you can always take the product measure that would satisfy this, but in general, there are many more measures on the product measurable space. So it's an admissible measure that fits into this graph or diagram, but it's not the product. So in order for this to be, so this category to admit products, there should be a unique measure here. But that is not necessarily true in general. And that's sort of like the issue. So when that happens, you call things disjoint, for instance. That's sort of like a rigidity. Yes. Yeah. So if I were to take two measure spaces, there's no natural way to take their products actually. So it's not, so the product measure is not a natural product, I'm trying to say. There's a society S from A alpha to B beta such that S refines T. So if I have any function T from A to the power set of B such that it is refined by some society, then T is also a society. And perhaps I should mention one other example to sort of like think of this constructively speaking. If I were to define a map like this, S of A for any A equals B. It's everything. So this is sort of like, this is trivially a society, but there's a lot of collisions in it. So you start excising collisions. As you keep excising collisions, eventually, I'm claiming here, that you reach a refinement that is in fact induced by a subcoupling, and then you can make it into a coupling. And vice versa, if you were to have a society, if you wanted, you could keep adding more points into its sets, and eventually, so whatever you add, extra you add, it's still going to be a society. So the point here is that there's going to be, given any society, there's going to be a minimal refinement. such that if you excise one more element, for instance, you end up losing the property of being a society. So this is going to be important in the marriage lemma. And in fact, let me also mention that. So now the marriage lemma let S be a society from A alpha to B beta, then there is, oh, this is in fact if and only if, but then there is a refinement R, let me put it like this. Then there's a coupling lambda of alpha and beta. It's not unique, such that the society defined by it, first of all, refines S, and second of all, its collision number. Yes. No, no, no. There's no uniqueness. And second of all, I think, so it has something to do with this procedure that you use to go from a society to a coupling that would define it. So there is some sort of choice involved there, and that's why it's not unique. S sub lambda, okay, then there's a coupling lambda of alpha and beta such that the society defined by this coupling lambda refines S, and its collision number is bounded by the number of elements in A. Okay. So if alpha and beta were standard uniform measures on finite sets, that gives you the standard marriage lemma that I mentioned earlier. Yeah. Okay. So when we're building this isomorphism in the Keane-Smorodinsky proof, what we're going to do is we're just going to say, okay, from the first guy, there's a society to the second guy. So there's a way to associate certain finite sets. These are called the filler sets of the spaces, of the shifts. We're going to say, okay, I'm going to take a society from certain filler sets to certain other filler sets. And then this machinery, combinatorial machinery, allows me to get a nice refinement of it that does this. And we're going to keep doing this for larger and larger finite sets that eventually cover almost every point in my space. And then because at each step we're doing this over finite points, finitely many points, this is also going to be shift invariant at the end of the day. So this is sort of like the idea. Like 6 or 7 minutes. I think, so okay. This, that, okay. I want to say a couple words about the proof of this statement because I think this is sort of the interesting thing here. And then I'm going to state one thing that reduces what we're trying to do to a specific case. Okay. So observation, this. Proof, or sketch of proof. So first of all, how to do this excision thing, first of all, I need, if I start with a society, I need first to be able to refine it in such a way that the collisions are bounded. So say there are 2 points, different, distinct points in A, and there are 2 distinct points in B, such that this happens. Okay? So you see, this would increase the number of my collisions. I want to decrease this. The way to do this is this. So this is this subset of B, and this is this other subset of B. I'm just going to draw Venn diagrams. And based on what I wrote here, I have one point here, B1, and another one, B2. So I'm going to define these functions. Oh, I have here. Take A, so S of A, if A is not AI, and take it to S of AI, take away BI, if A is equal to AI. So that means that, for instance, my R sub 1 of A1 is going to be the same thing, except avoid B1. So this guy is now this. Okay? And this is going to be everything. And likewise, I have another one, R2. There's R1 and R2. Both of these clearly refine S, but possibly they are not societies. But the observation is that at least one of them is a society. You say this is not a society. This means that alpha of some subset dominates beta of R1 of that subset. And using this, some combinatorics, very basic measure theory arguments, you realize that the other one has to satisfy the society property. So that's good. That allows you to excise one point at a time from your society to reduce the collision number. And eventually, you keep doing this sufficiently many times to reduce the collision number in total to a certain number. 3 minutes. So let's just say this. This is the idea first. So there is a, then there's a society. I'm going to apply it to something else actually. So let n be an integer. Define this new set b sub n, which is going to be b times n upper bar 1 to n, or under bar, it doesn't matter. Beta sub n is going to be a probability measure on the set. I'm just going to define it to be beta in the first one and R measure or uniform measure in the second one. I'm just going to take the product measure here. So beta of b divided by n. And I'm going to have S sub n from A alpha to Bn beta n, take A to the product of S of A times the whole second component. Applying this excision procedure, there is an Rn from A alpha to Bn B beta refining Sn such that with a low collision number. Let me just write it like this. Okay, so now define lambda n, a probability in the product by this. So this is a subset of B times n. I'm looking at vertical slices. I'm taking intersection, and I'm looking at how many of this finite set, this particular set hits. That defines a probability measure, and then you realize three things. One of them is that for all, so it's a probability measure first. Second of all, we have this. So this dominates when you push forward. Second of all, this also dominates like so. But also, because of this refinement having nice collision numbers, reduced collision numbers, I also have an upper bound here. And it's exactly, so I can make it such that I have this bound. So this is a collection of, this is a sequence of probabilities. Take a accumulation point of them. In the limit, you have a lambda. So accumulation point lambda. In the limit, you're going to have a lambda such that the B marginal, B push forward, is equal to beta. A push forward dominates alpha. But you can also realize that, in fact, it is equal. Note, so observe that lambda is, in fact, turns out to be a coupling. And certainly, if, and it's also an observation that S sub lambda is going to be a refinement of your original society. Okay, I think I'm out of time. I was able to discuss the main combinatorial part. Next time, hopefully, we're going to start going more into detail with the proof. Thank you so much for listening. Thank you. Yeah, do we have any questions? Yes. Yes. I mean, it's a standard cohomology theory that you use in dynamics. But let me say a couple. So and this is not a theory that Perry himself introduced. This was like known for quite a while. It was known, probably von Neumann knew it, perhaps in the context of unitary operators and stuff like that. But so how do you compute the entropy of a map with respect to a measure? You say, I'm going to first take a partition, let's call it alpha, of my space. And then I'm going to, so this is a certain value, and then I'm going to look at the maximum of this. So what is this? So the way they define this, so if you have a finite generator, this tells you, and so for instance, it was realized fairly early on that for instance, Bernoulli schemes, there is such an alpha such that you don't need to take the supremum. So you can just compute this value. And what is this? Want me to define this as this entropy of this. So I'm taking alpha, and then I'm refining it. So typically they use this notation for this. I'm using more categorical notation. And then I look at where elements go in one time and second time and so on. And then you can also realize that you can, given any partition, there's an information function associated to it. And indeed, this entropy value is the same thing as the integral of a certain function, L1 function, which is the information function associated to this partition. Let me call it Rf z positive of alpha Now, there's an alternative way of computing the entropy, which is by way of using the conditional entropy. And what you say is that entropy is the amount of information that you get today if you knew all the future. That is to say, this is equal also to the entropy of alpha given the future. And again, this can be written as an integral of the conditional information function. Okay. This is the information co-cycle. So this is an L1 function. It's an LP function. Let me just call this I. So I is the information co-cycle of mu f alpha. So this makes sense if you have a marked generating partition. And I can imagine this. So this is a certain conditional, right? So let me just write it like this. If you have this, this is the same thing as A in alpha chi of A of x, chi sub A of x, such times log of 1 over conditional of chi sub A conditioned on the sigma algebra generated by beta. Okay. And then when you sort of take the integral of this with respect to mu, it does generate this specific thing, which is the entropy. And so now we have I of p hat sigma x here, and likewise I of q hat sigma y from y to this information co-cycle of the first system, information co-cycle of the second system. But then, of course, I can pull it back if I had an Ash homeomorphism. So now I have this. And so you call two functions cohomologous. So I want these to be cohomologous. So let me write it like this. FGHI okay. If there is FGHIK, another function such that G equals minus SF, yes, minus K, up to a mu measure. This is sort of like this is modeled after group cohomology, if you want. Yes. Yeah, that's a co-boundary. Yeah, I can write it. Yeah. You can do this because in this case, the coefficients are abelian, but in dynamics, of course, we're really interested in non-abelian coefficients. I mean, sometimes you are interested in non-abelian coefficients, in which case you cannot write it like this. But in any event, so you see, people say that G is cohomologous to F by, so with K as a transfer. But of course, we have different regularities. The better this K is, the stronger the equivalence. So what I said there was that if your code length function, if two shift systems are Ash homeomorphic, then their information co-cycles are cohomologous with a bounded measurable transfer. And he also computes that for Bernoulli schemes, this cohomology equation never holds, unless the probability vector of the first guy is a permutation of the other one, which is a trivial case. Are there other questions? And also people in the chat. Yeah. Yeah, if you want to sort of like, if you're interested in these kind of things, probably Zimmer's book is the best way to start. Zimmer has a book called the Ergodic Theory, semi-simple Lie groups or something. It's like, yeah. He has something, he has a theorem called co-cycle superrigidity. It's related to this. Let's thank out. Yes. Thank you.